Hello all. Today we will discuss car engine management system. Engine management system has to deal with various types of sensor in the engine like speed sensor, temperature sensor, oil and pressure sensors, etc. So it monitors and gathers data from these sensors and continuously adjusts the fuel supply and injection timing. So the objective of EMS is to minimize the emissions and maximize the fuel efficiency and engine output at any given load. This is the block diagram of engine management system. There are various sensors, so we have to apply appropriate signal conditioning, means we have to filter the signal from these sensors and amplify this. Also we have to digitize those signals and then we apply to the microcontroller. Accordingly microcontroller takes the action and sends the signal to various actuators in the engine. Let us understand the operation with the help of animation.
The ECU is the Electronic Control Unit, or sometimes called the PCM Power Control Module, or ECM Electronic Control Module. It's the brain and it does the thinking. It works in a harsh environment and is subjected to temperature variations, electromagnetic fields and high vibration. First, we look at the sensors which input information to the ECU. Speed pickups are based on inductive or magnetic speed sensors. When a tooted ferrous wheel moves past the magnetic sensor, it excites a voltage in the pickup coil, producing an electrical analog waveform. The frequency of this waveform is proportional to the speed of the rotation. They are used for crankshaft, camshaft, and wheel speed sensors. The angular position sensor uses a resistor or potentiometer to determine position. As the wiper moves, the resistance is varied and provides a signal to the ECU. They are used for accelerator position and fuel level measurement. Temperature sensors use a thermistor which is sensitive to a change in temperature. It has a negative temperature coefficient. The resistance of the thermistor decreases as temperature rises. They are used for intake air and coolant temperature. When resistance decreases, there is an increase in current, which is converted to a voltage signal for the ECU. The hot wire mass airflow sensor, MAF, measures the flow of air into the engine. When we look inside the housing, we see an electric wire which is heated by an electric current and is maintained at a constant temperature. When the engine is started, current passes through the wire and heats it up. As the wire heats, its resistance increases and it limits current flow. An equilibrium point is reached between the heating effect of the wire and the cooling effect of the moving air. When more air flows over the wire, it is cooled. Resistance decreases, allowing additional current to flow until equilibrium is again achieved. The ECU uses the amount of electric current flowing to the heater to determine the mass of air flowing into the engine. It takes into account the temperature and density of the incoming air, and addition correction factors are not required. The NOx sensor allows the ECU to listen to the engine. It is based on a vibration sensor which consists of a piezoelectric element and is attached to the engine block. The energy from the vibrating cylinder block is converted into an electrical signal for the ECU. When the onset of the combustion knock is detected, the ECU will make appropriate alterations to the timing. The O2 oxygen or lambda sensor measures the amount of oxygen in the exhaust gas compared to the oxygen in the outside air. It generates a voltage from almost 1 volt in rich conditions to near 0 volts in leaner conditions, and the signal is sent to the ECU. The ideal air-fuel ratio occurs near the change from 1 volt to 0. For a petrol engine, the ideal air-fuel ratio is 14.7 to 1 by weight. Sometimes a HECO sensor is used. This includes a heating element which gets the sensor up to working temperature faster. We will now look at the outputs from the ECU. Ignition timing regulates the timing of the spark relative to the top dead center. A signal is fed from the ECU via a relay to the relevant HV coil pack, which is located on top of the spark plug. The coil pack transforms the signal to high voltage for the spark plug. Cylinder deactivation. On some cars it is possible to shut down some of the cylinders when not required, usually when cruising at light load. This is achieved by movable cam which is splined onto the shaft. When the cylinder is not required, the cam for both inlet and exhaust valve is moved away from the cam follower, leaving the valves in a closed position. A further development with the operation of valves is the camless engine. It does not have a camshaft and relies on electrical solenoids activated by the ECU to operate the valves. This allows immense flexibility with the control of timing and lift of both the inlet and exhaust valves. Fuel injection. Injects fuel according to inputs from accelerator, airflow sensor and common rail fuel pressure sensor. Fuel quantity can be varied by altering the length and number of fuel injector pulses. When operating in closed-loop control, fuel injection is determined by the exhaust gas-oxygen sensor. Most cars have separate ECUs for different control systems, with each CU having inputs and outputs. For example, the anti-lock braking system would have a separate ECU to the engine management ECU. All the information is transmitted between the ECUs using a bus system called a controller area network, or CAN system. Each ECU is programmed to accept relevant information if required. Example, road speed might be relevant to a number of control systems. Here we see an engine control system in operation. When the engine is started and still cold, fuel injection is determined from the amount of air flowing into the engine. The engine will have additional fuel and run rich. This is called open loop control. When the engine is up to temperature and cruising, the ECU will use the feedback from the exhaust oxygen sensor to determine optimum fuel injection, thus reducing emissions and fuel consumption. This is called closed loop control. If the lambda probe should fail, the control system will revert to open loop control as there is no feedback from the oxygen sensor. It will alert the driver via the engine management light. Fuel consumption and emissions will be higher, therefore the car should be taken to a garage for repairs. The OPD2 standard, Onboard Diagnostics 2, allows code scanners or data loggers to communicate with the ECU. Fault history and fault codes can be downloaded to determine which sensors are not healthy. Caution must be exercised when using a fault scanner, as quite often when there is a faulty reading from a sensor, the source of the problem might be elsewhere in the system. Also, high-resistance electrical cable connections can lead to erroneous readings, so check everything and as a last resort, change the sensor. Manufacturers program the ECU according to their requirements, and this information is a closely guarded secret. Normally, engines are not operated to the limit, and the designers allow a comfort zone, allowing for extreme ambient conditions or poor quality fuel. Recently, there has been an emphasis on energy efficiency and fuel economy. However, there are tuning companies which specialize in deciphering the program and modifying it usually to produce more power from the engine. This is often referred to as